It's different. All right, so a couple of things. First thing I want to tell you is that the final for this class is just a chapter test. It's not cumulative, it's just chapter 7 only. Why is that bad?
Oh,
Okay. It's basically the same length as all your other tests, it's just that you get 2 hours to do it instead of an hour and a half. So no need to stress about going back. It's just gonna be chapter 7. And it's holiday themed, so you have that to look forward to. The however, it is the last test that you can use a note card on. You can use your yellow sheet also, of course. We are going to be writing some new stuff on the yellow sheet this chapter. The yellow sheet will become increasingly important to you as you move on. Okay. Just so I got all of that on the video. Okay. The whole chapter is about sampling distributions. This is the title of the chapter. It's the first thing we're going to define. And if you walk away today knowing what a sampling distribution is, I would be happy. We're going to do two different, there's actually only one type of sampling distribution, but we're going to do it 2 different ways. We're going to do with a small population with John and Carol here, and then we're going to do with a very, very large population, which is all M&Ms in the whole world. So I just want you to imagine all M&Ms everywhere, every single one. It's kind of hard to, that's kind of a big population. Okay, so let's define a sampling distribution first. By the way, I missed you all. Thanks. Okay, the sampling distribution is a distribution. Nice. Ooh, I really solved a lot of mysteries for you there. Okay. The distribution of values. It's coming clear to me now. Taken, that's an N, from a statistic. Man, I haven't written anything in a few days. Feels weird. Okay, and we're going to list some possible statistics here that we might use. Mean is probably the most popular one. Proportion is probably the second. We're going to work with both of those today, but it could be anything. It could be IQR, it could be range, could be quartiles, could be any statistics. In all, this is the most important part. Possible samples of the same size in a population. Okay, and it's really easy to make a sampling distribution when your population is small. John and Carol have 4 grown sons. The whole population is 4 people. Okay, really much more difficult to make a sampling distribution for the population of all M&Ms in the whole world of sample size 20. You guys should have 20 M&Ms in your cup. I have everything crossed that you do. Please do not count them yet. I will give you plenty of time. Okay. So this is very important to all possible. And we'll get to that in a bit. This is the first lesson where I get to start teaching you about backwards stats magic. I'm going to say backwards stats magic a lot, and it'll make sense later. Okay, John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68. List all possible samples of size 2. Calculate the mean of each sample and use a dot plot to create the sampling distribution of the sample mean. Okay, there are a lot of words there, Mrs. Talbot. Okay, so we're going to go really slow here. And we don't know these people's names, so we're just gonna list them by their heights. Okay, so this is the guy that is 71, and he could be paired with the guy that's 75. There is one possible sample of size 2. So just pretend that all 4 of these slips are in a hat and you're picking out 2 of them. Okay, the 71 guy, he could also be paired with the 72. The 71 guy, he could also be paired with the 68. Are you guys picking up what I'm laying down? Okay. Now the 71 guy's kind of done. The 75 guy, he could be paired with the 72. And the 75 guy could be paired with the 68. And then the 75 guy's kind of done. And then the 72 guy could be paired with the 68. And that's it. That's all possible samples. Okay, so what we're going to do over here is we're going to find the sample mean of each one, and we're going to try to use mental math as best we can. So what number is in the middle of 71 and 75? 73, 71.5. You guys understand what I'm doing? I'm averaging these two. You with me? 69.5, 73.5, 71.5, 70. Okay, so the lowest one we have is 69.5, so I'm going to make 69, 70, 71, 72. Okay, label my axis. Okay. 73, 71.5, 69.5, 73.5, 71.5, 70. This is a sampling distribution. I want you to think about what things made this possible. It was a very small population of only 4 people. Can you imagine listing all possible examples of even like, if there was like 10 people to list? That would be a lot, right? I'm never gonna ask you to do that, I promise. But what made it possible? Okay, so we knew the entire population, we knew all of their heights. You need a lot of information to be able to make a sampling distribution. So I'm going to impress upon you that most of the time, if you're doing statistics, you're not going to be able to make that. We have very special circumstance. We have a very tiny population and we knew all the stuff about them. Okay, that's important. Do you have any questions about what we did? So we listed all possible samples. Okay, think about how hard that would be with M&M. Yikes. We found the average of each one, and we plotted all of the averages. Okay, we good? Okay. You guys are like, it's simple. Yeah, I know, but I care about you understanding it. You guys ready already? Maybe. Okay, so we're gonna make a second one. Same exact guys, John and Carol's fourth son. You can already start to list the possible samples of size 2. They're gonna be exactly the same as the previous one. It's just that we're not going to calculate the mean this time, we're going to calculate the range. And remember, range is max minus min. So these are all gonna be positive numbers. You just take the big one minus the small one. So to remind myself, the 71 guy could be with the 75 guy. 71 could be with 72. Okay, so I just listed the same 6 samples of size 2, all possibles. And now I'm going to do max minus min, which would be 4, 1, 3, 3, 7. Okay. 4. Okay. 1, 2. I made my dot plot, my line way too long. Oh well. I have to label it, otherwise it's gonna look weird. Okay. Four, 1, 3, 3, 7, 4. So my hope here is for you guys to see that you could do this with any statistic. If you wanted, you're interested in their standard deviation, if you're interested in their quartiles, it would be hard to do with 2. But basically anything, anything that you would want to calculate, you can calculate it for all possible samples and graph it, make a graph of it, and learn stuff. So does it make sense that you can do this for different types of statistics? We did mean and range as an example. Okay, does it make sense that I was only able to do it because I had a tiny population and I knew a lot of stuff about that? And you guys all understand that when I say sampling distribution, I'm talking about all possible samples. All right, okay, you guys are done in your notebook. We're gonna do the second half on the resource page, which is on the back of your stamp sheet for chapter 7. And this is where you're going to need your M&M's data. Okay. Okay, so the first bit is some vocab that I need to remind you of from chapter 6. We learned all of these words earlier in the year, but we need them here. So I want to remind you of what they are. Was it chapter 6? Or was it chapter 4? It was the one where I said, like, say what the sample is and then take out the number and put all. 4? Was it chapter 4? Okay, anyway. Okay, so I'm going to give you the same advice here. We're going to, I want you to think about all the M&Ms in the world. Okay, however, the easiest thing to start with is your sample. Okay, so the sample in this case is your 20 M&Ms in your cup. So what you're going to put is N equals 20 candies. Randomly selected. And I will tell you that I promise I did not look at the samples as I was counting them out. I just did it totally randomly, like poured them out of one Dixie cup into another. So I got as random as possible. Okay. So if your sample is size 20 candies, then the population is all candies. And you can say M&Ms if that. All candies everywhere. All candies, all of them. Just picture them in a waterfall. It's great. Okay. Now the parameter is a number having to do with the population. Okay, so the parameter in this case is the proportion of blue. So we're interested in blue candies in this particular activity. So the parameter is P equals the true proportion of blue candies. Okay, now I would like you to just identify what the parameter should be if, take a look at the paper here. I've given you the parameter, kind of, the supposed, the claimed parameter. Can you see it on the paper? 25%. I'm going to put it in a little cloud because they're claiming that it's 25%, but I bet you can imagine as they're coming off the assembly line, it's probably not always exactly 25%. Okay, and then the statistic is P hat. Okay, and remember, the hat, I know I'm videoing this, the hat, I always like to picture it as covering my ass. What I mean by that is, I'm saying that it's estimated. It's an estimate. I'm saying that I'm not sure what P is, so I'm estimating it with P hat. And I'm estimating it the best way I can by counting how many blue ones I have in my sample of 20. Okay, so at this point, if you could first make sure that you actually have 20 M&Ms in your cup, because Mrs. Talbot's special and I did this in a very short period of time. I brought extras in case anybody has 19 or gasp 18. Lexi, that is me. Okay, then somewhere over here, yes, you have, okay, don't worry. Okay, but you're gonna have to close your eyes and stick your hands away. Spicy. Anybody else have, did I actually do the rest of them right? Yeah. Okay, so count how many blue ones you have out of 20, and then put your P hat for your sample. Can someone do Sophia's, please? And Mariana's. Okay, now I'm gonna bring you a very unsatisfyingly not quite blue Post-it. I really wanted it to be blue, but this is as close as I could get. If you could please write all of the P hats from your table on the Post-it and then bring it over. So for example, mine would be 0.2. Feel free to use a calculator because it's been a long time since you divided anything. So we both have. All right, here we go. While you're doing that, create a graph of the population distribution. Okay, so over here, you're going to label this 0.1, 0.2, 0.3. Relative frequency, which just means proportion. Okay, and this is going to be a bar graph. So if I were you, I would definitely use colored pencils. I'm definitely going to use colored pencils because why not? I mean, we have to have fun. I know that most of you are seniors, but coloring is fun. Well, there's blue, orange, green, yellow, red, and brown. Okay, do you guys see where I'm getting my numbers from? 25% blue, 25% orange. Yeah. Okay, now on the second graph, you're going to do the same thing, but just for your sample only. So you might want to over here, like calculate all of them. I hope that you don't have 40% or more of anything because I only went up to 40% on this scale, but do you have more than 40% orange? Oh, wow. Yours look like Skittles. You do? I'm so sorry. Well, I wasn't sure how tall to make it. Oh, good. Okay. Real quick, before I make my bar graph, do you guys all understand that everyone in the rooms can have a different bar graph here? Okay. Okay, as soon as you get your sample graph done, you can eat them now. I'm coming around this Can you guys tell what we're gonna do on the number line? Yes, you're all set to eat them now.
When is the? Oh, yeah. Only two.
Yeah, it doesn't have to have a weekly feedback.
Good one. You have three.
That's all the files.
Can you guys make your dot plot, please? And thank you. Okay, now. This is a little bit different from what we did in our notebook. We went through the same process. We had a bunch of samples. We calculated some statistic. In this case, it was the proportion of blue, and we plotted them. However, this is a little different because we don't have all possible samples of size 20. It would be really challenging. I could spend the entire rest of my life trying to find all possible samples of size 20 from all M&Ms in the whole world, and I still wouldn't be able to do it. There's another problem too. This is clearly not all possible samples, right? We only have 24 of them here. And there's a chance that one of ours might have been identical to another. The only way to really get a sampling distribution that's perfect is by simulation. So by running like a million different, doing it like a software, that would be the only way you'd be able to do it. The thing that I need to tell you though, is it doesn't really matter because just this data alone will be able to give you pretty good information about the clay. Okay, so what I'm telling you to do now is shift your perspective. Say you didn't know what the claim was. Say you didn't know. You were just like, I wonder how many blue M&Ms there are. And you go out and you buy some bags of M&Ms and you take a bunch of samples. This gives you a really good idea of how many blue M&Ms there are without knowing the truth. This is what I mean by backwards stats magic. There are certain ways that you can figure out the truth by taking samples. And you can figure it out close enough to what you need it to be. It doesn't have to be perfect, but it gives you a pretty good estimate. You could tell from the center of this deal that, it's about 0.2-ish, which I think is pretty cool. So you can be lazy and find a few samples and use that to make a pretty good estimate of what's true. And that's basically what we're going to spend the whole rest of the year on. How can I be as lazy as humanly possible, do as little as possible to make an estimate about something real in the world that I don't want to count or measure or look at or any of that? That's basically what stats is. How do I be lazy and do estimate? Okay, so the first thing I need you to know is this is not a full sampling distribution. What we will call it is an approximate sampling distribution. And it's approximate because we don't have all possible samples and there really might be one that's identical. So we're going to call this approximate. And we're going to say to ourselves, that's not just good, it's good enough. Because it still gives us the information we wanted. It doesn't have to be perfect. It gave us some pretty good data in just a few minutes. Okay, flip the paper over. We have 2 questions to answer, then we're done. Okay. Explain what your p hat dot on the approximate sampling distribution represents. Okay, so what I'd like you to do is just go back to this spot here and circle one of these dots to claim it as your own. Mine I had 0.2, so I'm just gonna say this guy's mine. Just pick one. Just gonna say that one was Mrs. Talbot's. Any one of them, because you don't know which one was yours, but just pick one in the right column. Okay. What does it represent? The proportion of blue candies in my sample of size and equals 20. And it's really important that we keep saying that sample size because the sampling distribution will change a lot depending on sample size. And we're gonna explore that later in the chapter, but I just want to make sure we all understand we're talking about 20 M&Ms each time. Would you be surprised if you got a sample with P equals 0.25 or less? Okay, can you count for me how many dots are 0.25 or less? $21 out of 24 dots? Okay, is this surprising to you? Would it be surprising to you to get anything 0.25 or less? No. There it is, the R in surprise again. I'm always surprised that there's an R in surprised. We don't have enough evidence to say that it's not 0.25. It's very likely 0.25 from our graph. All right, I have a joke for you. Thank you. I mean, I don't know why I'm saying thank you.
Thank you.
Hmm. 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 Okay, real quick. On this first bullet point, these are my objectives for today. Distinguish between a parameter and statistic. Again, I told you this in whatever chapter that was, but I just want you to remember parameter starts with P and it goes with population, which starts with P. And statistic starts with S, which goes with sample, which starts with S. Population, parameter, sample, statistic. Okay, anyway, and here's your joke. Loch Ness Monster. Oh, it could be. Is it the good dinosaur guy? He's so cute. I love him.